Asteroids. Hurtling through space, they bring fascination and danger. Ask the dinosaurs. A meteorite the size of the Himalayas blasted them into extinction.
That was one of the biggest mass extinction and the evolution of the life on the Earth.
If such an impact would happen today, that could have very, very devastating consequences.
Asteroids regularly batter the planet and rattle our imagination, inspiring apocalyptic films such as Armageddon and Deep Impact. But fiction doesn't always remain fictional, like on this day in Russia in 2013.
Could have destroyed cities such as Amsterdam or Paris.
My goodness, I thought this is a science fiction, but it's really happening right now.
Even though scientists tell you that there is one impact every million years, it can happen tomorrow.
What are we going to do about it if we detect an asteroid that is coming towards Earth?
The search has begun. How many asteroids currently menace our planet and us?
Objects with a diameter of 10 kilometers can render an entire species extinct. Then you have bodies with a diameter of 1 kilometer. Those ones can cause a global disaster.
But there's millions of asteroids of very small dimension, so those are the ones we're really concerned about, and we want to be able to not only find them, but do something about them.
These near-Earth objects measure at least 140 meters in diameter, and we're in the danger zone for an estimated 25,000 of them.
Here we're talking about a regional or possible countrywide disaster. Their impact frequency is about once every 16,000 years.
For the last 30 years, international space agencies have been working on ways to protect the planet from a fatal impact. In 2022, NASA made headlines when it launched DART, the first mission to deflect asteroids.
I just broke down in tears. It was the culmination of 20 years of work.
Change the course of this asteroid forever. And this is all done by man.
This mission was the equivalent of taking a dart and launching it from Paris and aiming for something the size of an apple on the east coast of North America.
The Japan Aerospace Exploration Agency and the European Space Agency, JAXA and ESA, have granted a special permission to view asteroid samples collected 11 million kilometers from Earth, as well as witness the construction of the Hera satellite. Over the next hour, renowned planetologists, astrophysicists, and engineers will explain how we are preparing to avert the next apocalypse. The Earth, 66 million years ago. Dinosaurs ruled over a land made for giants. T-Rex, the biggest carnivore the planet has ever known, was king. But one spring day, this world came to an end. Thanks to a cosmic assassin from the deepest depths of space, an asteroid.
This was an asteroid that was more than 10 kilometers in size, that impacted the Earth at more than 10 kilometers per second. So this is a huge impact coming down.
That's one of the biggest impacts in the history of the Earth.
An asteroid the size of Mount Everest crashed into Earth in the shallow waters of the Gulf of Mexico with a force of impact estimated at more than 100 billion tons of TNT. 7 million times greater than the Hiroshima A-bomb. Any land situated within a 100-kilometer radius was erased from the map. Pulverized.
When a huge asteroid crashes into Earth, it's not the immediate consequences of the impact that lead to the extinction of a species or other such catastrophes. It's the longer-term effects of the impact.
So on Earth, we live in a biosphere that is very fragile. It might not seem so, but any change could just completely mess up with it.
20,000 cubic kilometers of rocks were ejected into Earth's atmosphere. That's 8 million times the volume of the Great Pyramid. This cataclysm began an unstoppable chain reaction which spread around the globe.
This ejecta extended extremely high. There was fire that was propagating to a large extent. These pieces of ejecta, they were falling back down and creating huge waves in the ocean.
The atmosphere increased in temperature and the planet became a furnace. Volcanoes were no longer dormant, but the worst was yet to come. The asteroid's impact brought about a phenomenon that was even more catastrophic.
And this huge event created such a large amount of dust and soot that was lifted up into the atmosphere that was then transported all around the globe.
It absorbs the sunlight, so the sunlight doesn't go through it anymore. And so the surface of the Earth, which is below this huge dust cloud, becomes colder and colder.
With an apocalyptic cloud encircling the globe, photosynthesis could no longer take place. Without energy, plants perished, leading to a total food chain collapse.
The animals that were still alive after the impact, they no longer had any food, and a large amount of the species on Earth were wiped out.
That was one of the biggest mass extinction and the evolution of the life on the Earth.
The asteroid's impact and its consequences led to the extinction of 75% of animal species. Among them, the most powerful to have ever walked the Earth. "66 million years later, the world has changed. As we can see from these images, asteroid threats are regular fodder for Hollywood blockbusters, and yet these tales don't just belong to the world of science fiction.
Are there objects that might one day hit Earth? And I think the answer to that question is yes, it will happen. The question is when.
It is devastating enough to really cause some major damage to the human civilization. So that may be one thing to worry about.
To understand why asteroids are such a terrible threat to our planet, we need to go back to the origins of our solar system. 4.5 billion years ago, space looked very different to today. The darkness was filled with a cloud of gas and dust known as the solar nebula. Until at some point, it collapsed in on itself under pressure from gravity.
What happened was this cloud of gas and dust started to condense, and as it started to turn, then all these little pieces of gas and dust, they formed a star.
That star is our sun. It became the central point around which matter from within the nebula started to turn, forming a disk.
And it's within this disk of gas and dust that the planets in the solar system as we know it today were created.
The external part of the disk, which was furthest away from the sun, was mainly made up of volatile matter such as ice, ammonia, and methane. Over several million years, these components formed the giant gaseous planets: Jupiter, Saturn, Uranus, and Neptune. And as these planets were formed, frozen bodies were expelled. Comets.
When they get close to the sun, these ice rocks sublimate. They go from solid to gas. This creates an explosion of dust, leading to these wonderful tails which can spread over tens of thousands of kilometers and which we can see from Earth.
And humans can look up and see this beautiful object in the sky.
The most famous is Halley's Comet, which crosses Earth's orbit every 76 years. This last occurred in 1986, when space probes collected images.
The tail is long, very spectacular.
So we know about the Halley's comet, but other comets, we don't have records of them.
The problem with comets is we discover them around the time they reach Jupiter, so about a year before they reach the Earth's orbit.
It's hard to track them until it might be too late.
Too late because comets are potentially hugely destructive, leaving chaos in their wake, as was the case for Jupiter in 1994. July 16th, 1994, a day that would go down in history as making the start of our understanding of their potential danger to our planet. 715 million kilometers from Earth, the first of 21 fragments of a celestial body with a diameter of over 2 kilometers Comet Shoemaker-Levy 9 collided with Jupiter at a speed of 60 kilometers per second. Over the 6 days that followed, 20 other fragments rained down on the biggest planet in our solar system with unimaginable force.
All of the telescopes were able to look at Jupiter during this event, and we could see the comet that had been broken up, creating enormous flashes coming from Jupiter.
If you look at the images, they're absolutely amazing. You will see Jupiter with these dots, black dots that are as big as our planets.
The biggest impact created a giant dark crater with a diameter of more than 12,000 kilometers. The energy released by the force of the collision was colossal. Roughly 6 teratons of TNT, or 600 times the world's nuclear forces combined.
So it was for the first time when humans saw what an impact can actually do.
My goodness, I thought this is a science fiction, but it's really happening right now. So I was like, well, this is not really like a fiction. It's a real story.
The impact of these titans on Jupiter helped experts learn more about the planet, but they also begged an important question. If this gaseous giant could suffer such an impact, could the Earth suffer the same? Could there be a follow-up to the dinosaur apocalypse which might threaten the human race or even the existence of our planet?
If such a comet was to impact the Earth, it would have been an extremely large event with global planetary scale consequences.
The simple answer is this type of comet is very rare. That's why, given how very low the risk is, it's not the #1 priority when talking about protecting Earth from an external impact.
Because these comets aren't the only kamikazes in the solar system to attack the planets. The collapse of the solar nebula also resulted in other celestial bodies which are much sturdier than comets. Asteroids. These enormous rocks are the foundations for the creation of the 4 other planets in our solar system: Mercury, Venus, Mars, and Earth.
Some ended up as planets, and others never increased in size. Were never absorbed into another planet and ended up in an area known as the main belt between Mars and Jupiter.
The asteroids in the main belt, they live their life, most of them stay there. But from time to time, things can happen in the main belt.
Sometimes they collide to one another and they change completely their trajectories, a little bit like a billiards game.
These collisions can push asteroids out of the main belt via exit routes. Most of them are absorbed by the sun, but others become a terrible threat to humanity and even our planet.
Those trajectories can have pretty different orbits and eventually come very close to the Earth. And that's when they can become a danger to our planet.
These orbits can sometimes be quite unpredictable. We don't always know where the asteroids are coming from or when an asteroid can come towards us.
We call these near-Earth objects, or NEOs.
Yeah, the near-Earth object is the most responsible impactor to the modern days of the Earth.
NEO orbits cross that of the Earth. For some of them, a collision is therefore inevitable. NEOs have already impacted humans in recent decades. In 1954 in the US, a woman was wounded at home when she was hit by a small falling meteorite. The scar from the impact stayed with her. 28 years later in the US again, an NEO pierced the back of a car in the middle of a street. In 2008, in India, another pierced the surface of the Earth in the middle of a rice paddy full of farm workers.
You're more likely to have a terrestrial accident than to get struck by an asteroid, but at some point it'll happen. That's why it's important we deal with the issue.
These big rocks might be dangerous, but they're nothing compared to those measuring 10 meters or more.
Those are the ones that we're really going to make sure that we know where they are and that we can try to protect ourselves from.
The best-known example can be found here in the Arizona desert. Created 50,000 years ago, Meteor Crater shows the size and force of impact of a huge meteor. The crater, with a 1.2-kilometer diameter and a depth of several hundred meters, was made by a 50-meter diameter asteroid. That's half the size of a football pitch.
And the extent of the devastation was out to tens of kilometers. By devastation, I mean things like the fireball, the hurricane-force winds, and the things that would actually wipe out any living species that might have been nearby.
It could have destroyed cities such as Amsterdam or Paris.
It's hard to tell whether people were living in the surrounding areas at the time of the impact. But these soulless destroyers have certainly killed people in the past. Not only did they lead to the extinction of the dinosaurs 66 million years ago, they've also been a part of human history.
It doesn't happen very often. But more frequent process that we should really worry about is a Tunguska-sized impact.
On June 30th, 1908, the Tunguska region of Siberia was hit by an asteroid 50 meters in diameter. According to scientists, the explosion occurred at an altitude of 9 kilometers, setting off a chain of catastrophic events.
It exploded in the atmosphere, and what hit the ground was a shock wave.
The explosion released between 10 and 15 megatons of energy, over 1,000 times more than the nuclear bomb at Hiroshima. The shock wave destroyed 2,000 square kilometers of forest. It was recorded by sensors in both Western Europe and the United States. The explosion created a huge flash of light, which spread through the night.
And the people in London could read the newspaper at night. It's much brighter than in the full moon.
Luckily, the asteroid fell in one of the least populated areas of our planet. Only 3 deaths were recorded, with many wounded.
We were very lucky because there weren't many casualties. However, if such an impact would happen today over a populated area, that could have very, very devastating consequences.
If it happened over Paris, that would be Paris wiped out.
The whole town would have just been flattened, basically, from this one event.
Such a disaster has not happened for over a century, but what's certain is that another Earth impact is inevitable. We know it will happen again, we just don't know when.
We don't want to have a Tunguska event in your hometown. So that's the practical thing to worry about.
We can't measure the frequency of previous impacts by looking at the Earth, because their traces are erased over time.
But there's another way to tell. By looking at the moon. 80% of its surface is covered in impact craters. Lunar impact flashes seen from Earth are the result of asteroids colliding with our planet's natural satellite.
What scientists have been able to do is to actually count the craters on the moon. And this allows us to estimate what is the asteroid population, how many asteroids of a particular size range exist in the space around Earth.
The results are fairly accurate.
The bigger the asteroid, the lower the frequency, because there are far fewer big ones than little ones. And the moon is our example to estimate the frequency on Earth.
On average, every 6,000 years, an asteroid with a 100-meter diameter hits the Earth, releasing energy equivalent to 50 megatons when it enters the atmosphere. That's equivalent to 3,850 Hiroshimas. If such a powerful cannonball were to hit one of our cities, it would be a major disaster.
There's always a chance for humanity to be hit by an asteroid. So even though scientists tell you that there's one impact every million years, it can happen tomorrow.
Those catastrophic events that could cause a major damage to the human society, I believe that those things should be really well prepared.
What are we going to do about it if we detect an asteroid that is coming towards Earth?
It wasn't until the Shoemaker-Levy 9 comet hit Jupiter in 1999 that the world started to grasp the real threat posed by asteroids. At that point, leading nations began to tackle the problem. The European Council came up with some first steps towards a solution in 1996. At the time, asteroids and comets were not well documented, and there was no approved way of changing their Earth-bound trajectory if they posed a threat.
Very few scientists were interested in asteroids, and we formed a team and we asked the questions, what does it make sense to do?
This is a threat, and a threat that needs to be addressed. And asteroid impacts are not one country's problem, it's an international cooperation.
And so that's when the planetary defense efforts really started to take place in the world.
It was decided an action plan was needed. It was divided into 3 stages. The first stage was to create an NEO inventory. Next, learn about how the NEOs behave and what they are made of. And finally, find a way to deflect them.
The risk of an asteroid impact is never zero. On the scale of one's individual lifetime, it's much lower than others, which is why we think it's not worth doing anything about. On the other hand, it's not zero, and the consequences are major. That's why we need to do something.
Asteroids are there. They are not going to go away, and asteroid impacts, they happen all the time. So it's not a question of if an asteroid impact is going to happen, but when.
The U.S. Congress was the first to launch a large-scale plan. In 1998, NASA was charged with creating an inventory of all NEOs over 1 kilometer in diameter, because 1 kilometer is Earth's disaster threshold. The asteroid responsible for the Tunguska event in 1908 was not detected by telescopes at the time. These retired space exploration tools could only detect stars at a distance of several kilometers.
We knew asteroids and comets existed. We'd observed them from Earth, we knew were there. But the progress that has been made since then is absolutely phenomenal.
The Pan-STARRS telescope in Hawaii can detect large numbers of asteroids thanks to its revolutionary technology. But the real star of the show is the Catalina Sky Survey. Launched in Arizona at the end of the 1990s by NASA, it's the source of more than half of NEO discoveries.
They look at a wide angle so they can scan the sky relatively quickly and essentially look for anything that's moving there.
That's when the number of asteroid discoveries really started soaring, leading to an inventory of 33,000 known NEOs.
And from space, another exceptional piece of equipment works in collaboration with its terrestrial partners, the American NEOWISE Space Telescope. It is Earth's guardian and has a vital mission.
The NEOWISE telescope is looking for dangerous asteroids, and so far it found 377 asteroids, out of which 63 are potentially dangerous to Earth, and we have to worry about them.
It's thanks to these observations, coupled with digital modeling techniques, that scientists can make asteroid inventory and estimate the number of NEOs based on their size.
Asteroids with the potential to wipe out an entire species are at least 10 kilometers in diameter. Their frequency of impact is on average once every 100 million years, and we are aware of all those currently on a path towards Earth. None are a threat on our timescale, so that's positive. Then you have bodies which are 1 kilometer in diameter. That's our planet's disaster threshold. It doesn't matter where it falls, the consequences will be global, and the frequency of impact, there is one every 500,000 years.
An asteroid with a diameter of 1 kilometer or 7 football pitches would therefore be enough to have an irreversible impact on the surface of the planet. Quite the bombshell, since there are just over 1,000 of these asteroids in our solar system.
We are aware of more than 90% now, and none of them will be a threat in the next century at least.
But there's millions of asteroids of very small dimensions. Those are the ones we're really concerned about, and we want to be able to not only find them, but do something about them.
These are NEOs with a diameter of more than 140 meters. Over 25,000 of these are estimated to pose a potential threat to the Earth.
And here we're talking about the disaster threshold of a region or entire country, depending on the speed of impact and density. The frequency of impact is roughly around every 16,000 years, but we've only identified 40% of these.
That means there's 60% of these asteroids. We have no idea where they are.
To be sure, it's best to know where they all are. That way, we know there's no short-term risk, and we can better anticipate long-term.
Except there's a problem. Technology may be progressing, but today's telescopes are still limited. To get round this, NASA has designed a one-of-a-kind telescope to guard the Earth, the NEO Surveyor Space Telescope. When it is launched in 2028, this impressive piece of equipment's mission will be to identify in just 10 years the remaining 60% of NEOs that are over 140 meters in diameter.
It's a game changer. It increased the confidence and then prediction of collision of small bodies to the Earth.
And that's great because it will also give us very precise orbiting details, so we'll be able to calculate impact probabilities even more precisely and anticipate the threat. We'll have solved the prediction part of the problem with this telescope.
But it's not enough to simply identify them. What can we do should one of these asteroids coincide with Earth's orbit? We only know about asteroids what our telescopes can tell us, as well as the few fragments of meteorite that have fallen to Earth. To better understand the threats they pose, we need to explore them.
This time, it's not just about looking at an asteroid, it's about collecting a sample to bring back to Earth.
Launched in 2003, Japanese space agency JAXA's Hayabusa mission has successfully achieved this great feat. For the first time in history, a man-made space probe managed to collect samples from a 540-meter-long asteroid called Itokawa, 306 million kilometers from Earth.
Oh my goodness, this is really the epoch of a moment of a creation of the new history of space exploration.
With asteroids, often we think, oh yeah, they're just little rocks. We can just do this or can just do that. Unfortunately, Mother Nature prefers to give us challenges.
The fragments arrived back on Earth on June 13, 2010, and the results of their analysis shocked the scientific community.
Well, we were expecting to find maybe just a monolith, like just one rock in space, but the picture was completely different. What we saw was basically an accumulation of rocks, a rubble pile.
This information is of primary importance when it comes to deflecting an asteroid. To find out more about these objects, JAXA launched a second mission on December 3, 2014. Estimated at more than $200 million, the space probe Hayabusa 2's mission was to collect samples from the Ryugu asteroid, a rock with a 900-meter diameter, located 309 million kilometers from Earth.
The Japanese thought, we'll use a 70-centimeter cone drill, just like a mosquito, and when the cone touches the surface, it'll trigger the release of a tiny projectile of 5 grams at 300 meters per second. The projectile hits the target, we collect the dust, and off we go. And with that, we can get at least a 100-milligram sample, which is our aim.
On February 22, 2019, all focus was on Hayabusa 2. In just 6 seconds, the cone took samples, preserving them inside a capsule.
Oh my God, this is great. Yeah, so that's only a simple thing. But the simple thing was really extraordinary.
The samples were sent here to JAXA's laboratory in the city of Sagamihara, Japan. Professor Tomohiro Uzui was in charge of the operation.
The biggest sample has more than 1 centimeter in a long diameters, and it's huge for us.
It was in this high-security lab equipped with the best tools available to modern science that scientists from the Japanese Space Agency examined this priceless treasure. Just preserving the samples was a challenge in itself. The smallest error could lead to atmospheric contamination, and the mission would have all been for nothing.
Passing through the window, we could see the samples, and also we could handle the samples by looking at the sample by naked eye, and sometimes we're gonna put the optical microscope on the top.
This data would help scientists to better understand the properties of asteroids with the potential to impact Earth and their role in the beginnings of life on our planet. What was once science fiction has now become a human feat of technology, which could help humanity in its battle against the destructive titans looming in the depths of our solar system. Because these NEOs are still heading full pelt towards the Earth, and we have no way of changing their trajectory.
In 2013, people actually became aware of how dangerous asteroid impacts can be. The sky just blew up, basically.
9:13 a.m., February 15, 2013. In South Ural, in the Russian city of Chelyabinsk, hundreds of people watched in astonishment as a cataclysmic event unfolded. The cause? The breakup of an asteroid measuring 16 meters in diameter at an altitude of 30 kilometers.
This was an impact that hadn't been seen coming. We didn't know it was going to hit.
It released 35 times more energy than the Hiroshima atomic bomb. The heat from the explosion could be felt within a 60-kilometer radius. The shock wave shattered the windows of buildings and houses. Roofs collapsed and thousands were wounded.
Luckily, nobody got killed, but it was a really actual example of humans could be hurt by the incoming object. So it really showed us that it's a real threat.
Images of the disaster were shared around the world. From that moment on, the world was aware of the danger facing our planet. The majority of governments finally started to consider what scientists were saying about the asteroid threat.
In the U.S., NASA's chief was summoned before the U.S. Congress to explain why NASA had not seen it coming. His response was, well, listen, if you'd given me the budget I've been requesting for years so we could work on this problem, maybe we'd have been prepared. And what do you do if something like this is heading for us? He replied, pray.
In 2016, 3 years after Chelyabinsk, NASA established the first Planetary Defense Coordination Office. A few years later, the European Space Agency followed suit.
We're trying our best to do these observations to predict these events so that we can have some warning system in place.
Even if we find an asteroid coming towards Earth, currently there's nothing we can do. And that's why we need a mission, we need some sort of mechanism to try to deflect these asteroids.
But how do you deflect these weapons of mass destruction? There are just two ways: destroy them or change their trajectory. Destroying an asteroid is the pretense of many Hollywood apocalyptic movies, like Armageddon, in which an asteroid the size of Texas threatens the survival of the human race. In the movie, scientists decide to destroy the gigantic rock by boring a hole into the center and placing a nuclear weapon inside to make the object implode. But is such an idea plausible?
I think a landing on the asteroid is possible, and then the drilling is also possible. So Armageddon type of operation, I think it could be done.
Something to consider as a last resort if other methods fail. Except that since it's a method that's never been tested, the consequences of such an explosion are unknowable before we've even thought about the secondary effects of using an atomic weapon.
We wouldn't use the Bruce Willis approach of planting the nuclear weapons inside the asteroid. It's not very well controlled. We may end up with lots of different fragments that are all containing nuclear material that are coming down to Earth.
Instead of safely deflecting, it could cause a little bigger damage to the Earth.
Using a nuclear weapon is therefore not top of the list. In fact, scientists would rather avoid it.
So rather than really breaking things apart, probably better to push to the side so that the asteroid really missed the Earth.
But how do you push something so colossal? Experts have tested several methods. Among them, the Yarkovsky effect, a gravity tractor, and a kinetic impactor. One technique that has been studied is known to scientists as the Yarkovsky effect. It's a natural thermal phenomenon in which sunlight plays a decisive role in an asteroid's orbit.
The Yarkovsky effect is a very, very slow effect that is due to interactions between the sun and the asteroid. So what happens is the sun heats up one side of the asteroid, and most asteroids are actually rotating in space.
While it rotates, of course, it exposes different areas of the asteroid to the sun. It absorbs heat and then releases.
Solar radiation irradiates the surface of the asteroid in the form of heat. This heat creates a force which can modify the NEO's orbit.
It's like jumping off a boat pushes the boat back. And in the same way, the radiation going in the direction of the sun pushes the asteroid away from the sun.
But this natural phenomenon is only really effective for small asteroids with a diameter of less than 1 kilometer. In addition, the change in orbit happens extremely slowly. However, scientists think it might be possible to control the effect in order to change an NEO's trajectory.
There are some who think painting the asteroid is an option to modify its thermal properties and therefore change the Yarkovsky effect in order to change the asteroid's trajectory. I don't know what painter we'd send, nor do I know how we would paint it or how could we make sure the paint didn't evaporate or how to get it to stick.
This is something that potentially in the future one could try, but I don't think that today it's considered as one of the most optimal methods for trying to deflect an asteroid.
Because a simpler option does exist, a gravity tractor.
The gravity tractor is a most gentle way of deflecting an asteroid.
This technique involves sending a space probe to fly close to the asteroid in order to gently alter its trajectory thanks to the gravitational force generated between the two objects.
It doesn't touch the asteroid, just gets close to it. The asteroid's here, the probe is here. And I use the mass of the probe to attract the asteroid towards it.
The gravitational attraction of the spacecraft pulls the asteroid and therefore changes its orbit. We need to be extremely careful, of course, not to deflect an asteroid in a direction that one day makes it hit Earth.
Except you need to put several elements in place for it to work.
The first is to have a spacecraft that is as massive as possible to generate enough gravity to pull the asteroid towards it. And the second thing is a lot of time, because the gravity pull is so weak that you need decades really to change the trajectory of an asteroid.
Using this method, a 20-ton spacecraft could sufficiently deflect an asteroid by 200 meters if it traveled close to it for a year, as long as the operation was carried out 20 years before expected impact. Experts wish to test this method, the advantage being that it is a controlled deflection.
So despite this being one of the concepts that has been studied by the scientists, it was commonly agreed worldwide that the kinetic impactor was also the most mature technique and the first one that could be validated.
The kinetic impactor technique is a very elegant technique. You don't need any explosives, you don't need any science fiction technologies.
Basically, this is when you have a spacecraft that's going to drive into an asteroid at very high speed and just push it off its course, a bit like when you're playing snooker.
The spacecraft will end up its course there and change the velocity by only a few millimeters per second. It's nothing. But if you do that early enough, even on a huge mass, that's enough to miss the Earth.
5, 4, 3, 2, 1. November 24th, 2021. SpaceX's Falcon 9 rocket, launched by NASA, took off from the Vandenberg base in California on a pioneering mission never before seen in the history of mankind. On board, a $300 million technological jewel programmed to deflect the DART kinetic impactor.
The DART mission is a probe that weighs over 600 kilos to start with, which has propellers, solar panels, and a camera which will help it stay on course. And it's equipped with an intelligent navigation software which will help it hit the asteroid.
We wanted to show that we were capable of moving a body in space. Okay, so to do that, the DART mission targeted a binary asteroid.
This binary asteroid is a mini Earth-Moon system. Located 11 million kilometers from our planet, it's made up of one big 800-meter diameter rock named Didymus, around which a smaller rock, Dimorphos, with the surface area of a football pitch, is in orbit. The DART probe needed to hit this rock with a diameter of 150 meters.
We're talking about something very small. And when the probe got there, it was going to see the big rock first, and it was imperative it didn't hit that one. It had to hit the little one. So it had to be able to distinguish between them and focus on the little one.
This mission was the equivalent of taking a dart and launching it from Paris and aiming for something the size of an apple on the east coast of North America.
September 2022, 10 months after launch, the DART probe closed in on its target, a triumph in itself.
And those final hours were what really counted, because the challenge was that until we saw the object, we had no idea of its shape.
But the engineers had thought of everything. They had equipped the probe with a high-performance innovative camera. Named Draco by its designers, it was the eyes of the DART spacecraft.
Fantastic instrument, extremely detailed, that even coming at such a high velocity was able to download thousands of images at a very, very fast rate, almost real time.
The images it sent back were a world first. In the operations room in Baltimore, USA, time stood still.
All the images taken by the DART spacecraft are broadcasted on Earth, so we can see everything that is happening. And what we see 4 hours before the impact is just dot. And then as time passes, we start to detect how the shape forms.
It was the first time we could see from 10 million kilometers away images real time. This was incredible.
We were able to see the images as Didymos appeared, and then as we got closer and closer, finally as Dimorphos, the moon, appeared in the field of view as well.
Dimorphos. The mission's target appeared before the scientists thanks to the Draco camera.
Even myself being an engineer and not a scientist, I was blown away, absolutely blown away.
For us, it was a great moment, but we couldn't afford to miss our mark.
Not being able to target the asteroid would just mean that the spacecraft flies by the asteroid and the mission is done, or would just have to wait another 4 years or so to impact again.
To avoid that terrible outcome, the engineers had designed a revolutionary technique using an extremely sophisticated, high-performance onboard system. Until that moment, the DART spacecraft had been piloted from Earth. Now the probe was traveling independently using artificial intelligence.
Impossible to do anything from the operations room now, so the software was guiding itself.
The computer is calculating exactly the push that needs to be done to be in a certain point at a certain time. So you have this constant targeting until you get close, and then the surface becomes bigger and bigger and bigger.
You're approaching the soccer field with 6 kilometers per second or roughly 20,000 kilometers per hour. So it's amazing.
To film the results of the impact, the DART spacecraft released a small satellite the size of a shoebox equipped with a camera. Developed by the Italian Space Agency, the tiny Lishaku probe needed a front-row seat to broadcast images of the collision to Earth.
So it's not only a matter of putting your cell phone camera in there, it needs to be very well calibrated. It needs to be focused, and it needs to look at stuff that are 70 kilometers away. So it's not an easy feat.
September 26, 2022, 11:13 p.m. Greenwich Mean Time. Scientists and engineers alike were preparing to experience a unique moment, which would go down in history as the world's first attempt to redirect an asteroid. NASA broadcast the event live around the world. In the operations room in Baltimore, everyone held their breath.
It's one of those incredible moments when you're both super excited and you're also scared it's not going to work. And so the whole team was waiting. And then we received the first images.
On a eu les premières images.
What's going to happen? Suspense. Huge suspense. Levels of excitement at their peak.
We start to see more and more pixels.
Energy and their time into this, so much planning and rehearsing.
It's breathtaking. We've been working on this mission for 20 years. The moment we saw these images, we were all crying. It's nothing like we've seen before.
And at about 2.5 minutes out.
The last image that was transmitted from the DART spacecraft was a partial image. It was just a bit. But we saw that it just went straight in the middle of the asteroid.
2.5 minutes out.
It's 1:14 a.m. The DART probe hits the asteroid Dimorphos at a speed 6 kilometers per second, 24 times the speed of a commercial airplane.
I just broke down in tears because it was the culmination of 20 years of work.
For the first time, the whole world celebrated losing a spacecraft because we lost it exactly in the moment we wanted and in the place we wanted.
The first results were incredible. The kinetic impactor hit the asteroid just a few meters from target. But the first images sent in by terrestrial telescopes worried the team.
We saw images of the ejecta coming from the asteroid, which was amazing because we did not expect that.
We were quite scared when we saw those images because the small asteroid just looked like a fireworks display or something.
At that point, I thought, oh no, we've pulverized Dimorphos.
There was 1 pixel that we could see, which told us, okay, the asteroid is still there. We haven't destroyed it. It's good, all good.
All was well after all, and they could celebrate their moment of glory. The mission's objective had been achieved.
We change the course of this asteroid forever. And this is all done by man.
On top of all of it, it wasn't just for fun. We were really learning how to protect the planet.
Et puis on vous reparle de cette mission digne d'un scénario d'Hollywood.
An asteroid traveling at 14,000 miles an hour.
Tonight, the final seconds before that spacecraft slam into that asteroid nearly 7 million miles away. The view here.
This achievement provided a convincing technique for blocking an asteroid, except that it only worked for asteroids that were a few hundred meters in diameter at most, like Dimorphos. If an asteroid that was 1 kilometer in diameter was heading towards Earth, the technology would most likely be ineffective.
It wasn't a one-fix-all solution, but it was still a big deal that we'd managed to achieve that.
However, the story is not over. And that is because we want to see what happened.
And this is where the European component, the Hera mission from ESA, enters the picture.
Run by the European Space Agency, the Hera probe will lift off in the autumn of 2024 and fall into orbit around Didymus towards the end of 2026. It aims to inspect the state of Dimorphos and take some samples to understand the consequences of the impact.
When the DART probe deflected the asteroid, we could only measure a part of the effects from Earth. There are so many questions we need to answer to help us validate this as a technique.
To basically make sure that this impact has been efficient and effective enough to be used again in the future on other asteroids that could pose a potential real threat to the Earth.
More than 500 people from all corners of Europe have helped design this masterpiece of engineering. Built in a record 4 years, Hera was assembled here at the European Space Research and Technology Center in Noordwijk in the Netherlands. ESA has granted a special permission to film the satellite.
What you can see here is basically the core of the satellite. You can have a look to some of the key equipment that allow the satellite to work.
This cube, measuring 1.6 meters across per side, contains more than 7 kilometers of cables, which are all perfectly linked to give Hera complete autonomy. 13 meters squared of solar panels will provide electricity, but before it can launch, the probe must withstand a battery of tests where there's no margin for error.
We do a series of tests to verify that the spacecraft is ready, can withstand the launch, and can withstand its operational lifetime in space.
When it launches, the probe must be able to withstand the rocket vibrations. It's an ordeal that can damage the structure of the satellite if it's not been perfectly calibrated in advance.
This is an unbearable sound level. We have these huge LED doors. Those will be shut before starting the test. The spacecraft will be put in the middle of the room with some sensors. And then we will switch it on. A lot of nitrogen will flow to that pipe and will create an unbearable noise level.
Hera will then be put inside this black cube to experience the intense conditions of a space vacuum as well as extreme temperatures.
We will close this big tank with this very heavy lid that will hermetically seal the chamber, and then we will pump down the air lowering the pressure down to levels similar to the ones that you have in outer space.
The on-site exploration will last 6 months. The entire surface of Dimorphos will be mapped. Its mass will be estimated with great precision in order to therefore have a direct estimation of the effectiveness of DART's impact. Using nanosatellites which can land on the surface, HERA will be the first mission to measure the internal structure of an asteroid.
With the technology development, they become more and more powerful. And today they're really interesting instruments because you can think of them as drones that you deploy when you get to your destination.
That will help us having complete image of the impact itself, of the system before the impact and after the impact.
It's a promising mission, which could tell us whether our first attempt at asteroid redirection is effective enough. In addition, it will help us to find out more about the creation of the solar system and the beginnings of life on Earth.
We have the potential to learn a huge amount from asteroids. The missions we've had in the past and that are still ongoing have taught us so much about where we came from and about how the Earth was made up and other planets and planetary formation in general.
In the meantime, on April 13th, 2029, 2 billion people in Western Europe and North Africa will be able to watch a 370-meter diameter asteroid pass over Earth with the naked eye. Named Apophis, it will travel between the Moon and the Earth, close to our geostationary satellites.
It will be a global event, and here in Europe, we're trying to organize a mission to go see this asteroid as it passes close to Earth.
Scientists hope it will help the world to understand the presence of asteroids in our solar system. Not only are they fascinating objects, these interplanetary rocks could also be the source of our extinction if we don't find the technology to deflect them in time.
We're buying ourselves a life insurance policy that we'll be able to give to future generations so that the day they're faced with this, there's an established protocol so that they won't have to argue about it, think about who does what and how, because they already have a tried and tested method they can use and say, okay, this is more or less right and we can avoid this happening. That's our aim.
Crucial for humanity and for our planet if we wish to avoid an apocalypse.